Hello friends, today we are going to discuss about modeling analysis and design optimization of a mechanical component. So what we'll do is, in this case, we'll select a component, hanging plate of length 120 millimeter and breadth 50 millimeter, height 25 millimeter, and on the top of the base plate a load of 5 megapascal pressure will be applied and it will be hanging through a hole. After that, based on Brown-Weiss criteria, we have to check the optimization. We have to minimize the mass, by the same time we have to minimize the stress also. Not minimize the stress, we have to select a specific range of stress. And here this is giving us here it is given that modulus of elasticity equal to 2 multiplied 10 to the 5 Newton per millimeter square and Poisson's ratio equal to 0.26. We'll be using SolidWorks software for doing this modeling, analysis and optimization. Okay, then let's get started. So first of all, we have to start SolidWorks. So already started. First of all, we have to start from this part 1, new part we are opening. It's taking a little bit time because maybe the laptop is a little bit slower. Now see one thing, here the unit is millimeter gram second, and lower right corner you can see millimeter gram second. You can change the unit if you require, but this is standard one. We are taking millimeter gram second. If you like, you can go for MK, CGS or FPS system, but selection is taken millimeter gram second. Correct. Now let's see the drawing again. The drawing is a base plate with a hanging side wall. Base plate is a rectangle with length 120 and breadth 50 millimeter. So we can see the drawing. We have to start from the top plane. Select top plane, normal to, then we have to start from sketch. We are taking the rectangle one, drawing the rectangle without any dimension. Now let's provide smart dimension. Length is 120 millimeter and breadth is 50 millimeter. Drawing is complete, so we have to go out of the sketch. We are exiting from the sketch. Next, select the sketch and to start with features. Features extrude boss base, and the extrude thickness is 25 milli. Object is extruded. The base part is complete. Now let's see the drawing again. Back side, we have to make a side wall of height 50 millimeter and OD 25 millimeter radius and ID 25 millimeter diameter. Let's get started again. So we have to go back side, select normal to, again starting from sketch, center line, draw the center line. Now here you have to draw the circle. 2 concentric circles are required of diameter 50 and 25. First we are drawing diameter without any dimension. Next we have to draw some lines. We can draw the lines by tracking. Okay, drawing is complete. Now before going any kind of extrusion or extrude or whatever thing, you have to make a closed drawing. So this part we have to trim out. You can trim out, trim entities. Okay, now we have to keep dimensions. Smart dimension, radius of this one equal to should be 25 milli. In our diameter is 25, and height of this one will be 50 milli. drawing is complete. Okay, right. The next one, what? Let's see the drawing again whether it is 50 or not. Yeah, this is 50. This is radius 25 and inner ID is 25. Drawing is complete. As the drawing is complete, you have to go out from the sketch, exit the sketch. Now select the sketch and features extrude borders. Now when you are extruding, you can see it's going back side, so we have to reverse the direction. And extrude thickness is 25 mm. Reverse the direction, extruded. Done. Let's see the drawing again to confirm these things. Yeah, here radius, fillet radius 8 mm. Here also 8 mm radius. Select this edge and control, select the opposite edge. It's not selecting, select this one, and both are selected. Now fillet radius is 8 mm. Done. Drawing is complete, right? Okay. So next part, what we have to do is we have to go for analysis. What we'll do, we'll make the whole part fixed and we'll apply a pressure of 5 megapascal on the top plate here. Let's see whether it is failing or not, right? Okay. Now for starting analysis, we have to start with simulation. Study, new study. Okay, right. Next part, we have to apply module material properties. We have to apply material properties. Part, apply edit material. We have seen in the question that modulus of elasticity is 2 into 10 to the power 5 Newton per millimeter square. That is 2E5, and Poisson's ratio is 0.26. We'll select the same way. Let's see. You see here A36, modulus of elasticity is 2E5 and Poisson's ratio 0.26. So we'll select this one. Apply, close. Material property is already given. Next part is we have to apply fixture. That means we have to fix the central hole. Fixture. For fixture, we are having a lot of different options, but easiest option is fixed geometry. Another option can be taken as like advanced fixture. We can select, but here easier option is fixed geometry. Select the whole part. Okay, it is selected. Now next part is you have to apply load or pressure on the base plate. External load, pressure. Here pressure unit is Newton per meter square. That will be changed to Newton per millimeter square. How much amount of force you have to apply? Let's see the question again. It is, I think, 5 megapascal pressure to be applied. Okay, so we are applying pressure of 5 megapascal on the top base plate. Done. Pressure is applied. Next, the last part, we have to mesh and run. Analysis has already been started. Is going on. Okay, we have found the final result. Here the yield strength is 2.5 10 to the power 8 Newton per meter square, and 1 measure stress, maximum stress developed inside it is 1.71 10 to the power 8. Better to analyze a better way, we can do one thing. We can change the unit. Edit definition. 1 measure stress, unit is Newton per meter square. That will change to Newton per millimeter square. That is megapascal. Done. Okay, let's see this one. Yeah, yield strength is 2.5 into 10 to the power 02. That is 250 megapascal yield strength, and maximum stress developed equal to 1.71 10 to the power 2. That is 171. That is, stress developed is much below the yield stress. That means design is safe, and we can find out how much is the factor of safety. Actually, factor of safety equal to yield stress divided by the working stress. It will be definitely, you can see it is really definitely more than 1. Let's find out this one. From here also we can find out the modulus of your, let's find out the factor of safety. How to find out? It will be starting from result advisor, new plot, factor of safety. Okay, done. It is showing factor of safety minimum is 1.462 and maximum is 2.9 10 to the 3. It is very high, right? So it is safe, but the thing is, high value of factor of safety means it is the wastage of material. Anyway, the object is safe, our design is safe, and factor of safety is 1.4. That is good enough. But better to have increase this factor of safety a little bit more. We want to have factor of safety to be 1.5, or we can do one thing. Our stress developed was 171. We'll do one thing. Stress developed inside this object we want to fix at 150 megapascal. This will be our task, right? Now we have already done analysis. Let's see the result of the analysis things. First we'll see the stress already done. This is the stress. As I told earlier, the maximum stress developed is 171 and yield strength is 250 megapascal. Now we can check stresses at different places by the probe. By right button of click a mouse, you can see probe is coming. Now whenever we click anywhere, that will show the node number and the stress developed. Actually the red places, red marks are having more stresses. You can see here is the maximum stresses. If you click here, it will show that point is having node number 792 and value of stress is equal to 1.6 10 to the 2, that is 166, which is below the yield point. So it is safe, but it is very high compared to the normal stresses which is showing by the blue colors. Let's click another point here. That point is having node number 1184 and stress is equal to 133. That is also safe. Let's see here again. Here it is, stress is 163. Let's see the blue color, it is a very less one. It is 1.29 into 10 to the 1, that is 12.9. Is very less. So we have checked the stresses at different places, right? Our area of concern is this fillet where the stress is little bit higher, though it is safe one, right? Next, what can we do is we can go for result comparison. Compare the results, it will show stress, strain, displacement by the same time, or that factor of safety also. Let's see this one. Is already started. We can see first one is von Mises stress. Second one, we go downside. We can see this is displacement, and top right side is strain, and downside is having factor of safety. These are the result comparison, right? Okay. Now I'll close this one. Another thing you can see, like when we are applying pressure on the base plate, how the model will animate, how the model will vibrate. That can be checked again. From here, animate. See, the hole is fixed and the base plate is vibrating, right? Let's close this one. So we have got little bit of idea about design analysis. So from here we can find out the yield strength of the material is 2.5 multiplied 10 to the 2, that is 250 megapascal, and maximum stress developed, it is 171, which is much below the yield strength. That means the design is safe, right? Now we want to go for optimization. In optimization, our task will be, we want to minimize the stress again. We want to minimize the stress, not minimize the stress, we want to bring down the stress to a little bit lower. Initially it was 171, I want to come down to 150 megapascal. By the same time, our another goal will be to minimize the mass, right? Okay, let's get started. Now for design optimization, what can you do is, we start from static, down, left side, bottom side, right button of mouse, we can go for create new design study, right? In new design study, what we'll do is, new design study, we have to select some specific parameters with some specific ranges, and with different ranges of those parameters we can go for design study, and with lot of different permutations and combinations we can find at which parameter, at what different parameters the mass is very less, and by the same time stress is also less. So what we have to do is we have to select those parameters which is responsible for reducing the mass by the same time reducing the stress. Here we can select all the parameters, but better to take which one is changing stress value much more. Those things we should check. Actually stress value is much more at the fillet section and also near the hole position, right? And if you want to reduce the mass of the whole object, then thickness of the base plate also can be reduced. Now see what parameters are coming down. We have to select the parameters from these variables, click add parameters, right? Okay, now we'll bring this one a little bit downside. Now see what are the parameters. First one is the height of the base plate. This one we can select. Okay, done. Now the name of this base plate height, we can note down base plate height. Name is base plate height given. Now another parameter we have to select. The radius, fillet radius we will select. Give the name as fillet radius. Fillet radius given. Okay, another parameter you can take. We have taken this base height and fillet radius. As we have seen, the stress at the inner hole diagonals was little bit higher. That part we can select. So how to select that one? This one. Done. Any other thing we can take? We can take a lot of things, but other things I think not required. These are enough. You can do one thing. Height of this one was how much? 50, right? Height of this one also can be taken to reduce the mass. Height is having some importance. To reduce the mass, height to be reduced. Let's see. Let's take the height again. Done. All the parameters have been selected, right? Okay. Now what we'll do is these parameters we want to provide some specific ranges, right? That to be started from here again. Height, height minimum is 25 and maximum is 75, right? Next one, base plate is also selected, minimum 12.5 and maximum is 37.5. ID minimum is 12.5, maximum is 37.5, and fillet radius minimum is 4, maximum is 12. Okay, done. Next part is we have to provide the range of stress. Should be minimum, not minimum, it should be below 150. We have to fix it. Initially it was 171. We have to fix the stress level 150. How to do this one? It will be coming from constraints. Add sensor. Now here we have to select simulation data. Stress, one measure stress. Here the unit is PSI, pounds per square inch, that to be converted to megapascal, Newton per millimeter square. Okay, done. Now we have to specify the range of the stress. It should be less than 150 megapascal. Okay, fixed. Now the final goal. Final goal is what? Final goal is you have to minimize the mass. It will come from goals here, down, add sensors. Now see here, the original mass is 225.4585 gram. Original mass is 225 gram. Our task is to minimize this one. So what we'll do is select the object and OK. Minimize the mass. Okay, so all steps completed. Now see here we have done 81 numbers of scenarios have been taken care of. That means 81 numbers of iterations will be going on to get our optimization work. It is okay, we can change these values also, like different ranges. If we change the different ranges, numbers of these scenarios can be varied. Now one thing is very important to say, that our optimization may not be achieved also. Why? The reason is, what ranges we have selected, maybe optimization is requiring more data, maybe the range is not enough to get the optimized one. So what default value of ranges it has provided, we have started from this one. I think it will be done. If it is not done, we can go for another optimization with different ranges. Let's see this one. We are running the optimization database. It will take some time. One is going on. It will take some time, near about 5 minutes it will take. Now you can see it is showing 7 out of 83 scenarios have been taken care of successfully, and design study quality is high. Now another thing to be seen here, that the drawing is also changing. That means the object is also changing. As the parameters are changing, object is changing. By this way, 83 numbers of iterations are going on with the different parameters, and all cases it is calculating the mass and by the same time stresses also. Optimization is going on. So we can check here, it is like 27 scenarios we have got warning, that means analysis failed in 27 cases, and 53 out of 83 scenarios ran successfully. So design studies quality is very high. We have finished. So design optimization is done. We can check the values right now here. The initial value of base plate height was 25. Optimized value is 12.5 millimeter. Height was 50 millimeter. Here height was reduced by half, that is 25 millimeter. ID was 25 millimeter. But in this case, to reduce the mass, we had to increase the ID. It is 37.5. And fillet radius was 8 millimeter. We have already seen that fillet radius is 8 millimeter, and at that point stress value was very high, so we have increased the fillet radius by, now the fillet radius is 12 millimeter. The stress initially it was 170.95, now it is 130.93. It is very less. That is, factor of safety is improved. How much will be factor of safety? It will be 250 divided by 130. That means near about 1.9 something else. And the mass, initial mass was 225.459 gram, and it is 163.371. It is much amount of material is saved. So this design optimization is successful, right? Now we got the design study. Finally, after this one, we can save all this work and generate a report, right? We can save this part in the desktop. In the desktop we have already created a folder. There we can save it, right? Okay. This is all about our design analysis and optimization of a mechanical component. So from this one, what we found? We found that we created an object using SolidWorks, and we applied a load of 5 megapascal on the base plate. In that case, maximum stress developed was 171. Then after optimization, we found the minimum mass. We reduced the mass, and final mass is 166 gram, and the stress also reduced to 130.93 millimeter per millimeter square. Okay, thank you.